Hello. In this video, I'm going to solve this problem involving this person that is pulling this cart of mass uh, MB um, up a hill and with this pulley thingy around a rope. Okay, so the first question, one, asks us what tension the person needs to pull with to lift the box up the hill. We're going to assume that it rolls frictionlessly. So we would like to know that. Okay, so we can draw the free body diagram of this MB. So it's going to have gravity downward, MBG. It's going to have normal force off like that, and it will have two tension forces, TT. Why is that? Well, if you look at it, it's got a tension force pulling up here and a tension force pulling up here. So it has double tension pulling it up. Okay, so basically what we can do is we can do this the sum of forces in the x direction where we set x to be that way. Okay, so sum of forces in the x direction equals MAX. Let's see. What does this problem say about AX? Pulley at the top. Okay, so I'm going to assume that all right, it says right here, constant speed. It's walks up. So the person is walking down the slope at a constant speed. So the box is going to go up the slope at a constant speed, meaning that the acceleration is 0. Okay, so I can do the sum of the forces in the x direction. Okay, the sum. So let's do that. That's tension. Well, two tensions actually, because there's two of them in the x direction. Minus MBG, and it's either going to be sine or cosine. Which one is it going to be? Okay, well let's see here. I want the component of mg that is so that is the angle theta there. If that angle is the same as this angle. You can tell that because it's that this angle gets small, this angle gets small. So if that angle gets small, then this here is sine. Okay, so it's equals to, or mg sine theta is equal to 0. Okay, that makes the tension equal to MBG sine theta over 2. Okay. Now let's move on to part number 2. Okay, now part number 2 says to pull the box a distance L up the slope, how far does a person need to walk downward or backward? So if you go back to the picture, box is going up, person is walking down. We're going to go up a distance L like that. How far does the person need to go down? Well, for each foot the person walks down, it pulls a foot of cord over the top of this thing, which will shorten both of these. That foot has to go, some of that foot will go into shortening this cable, and some of it will go into shortening this cable. So in other words, the person has to walk twice as far down the hill as the cart comes up the hill. So 2L. All right. Question number 3. What is the net work done by the person pulling the box a distance L up the hill? So this is the net work, meaning work that the person does minus the work that the gravity doesn't have. Because like as the person walks backward, gravity is pulling them downward. So gravity is actually doing positive work on the person. So the person is receiving work from gravity, and it's doing work on the cart, and we're only just trying to do find the network, aka how much energy is the person's muscles going to have to expend. If the person is heavy enough, he could just slide down the hill and pull the cart up. It wouldn't take him any energy. But we're going to assume the box is heavy enough that the person has to do work pulling the box up the hill. Okay, so we could do this using force times distance. we could do that. Let's do it. Let's do it that way. So work is equal to force times distance. So force, we have this force is pulling the person. So it's force times delta x. So this is the force of tension pulling the person up the hill. But gravity pulls down the hill. So the net force that the person has to push on, with their feet on the ground, is the difference between those two. So it's mb g sine theta over 2 minus m person g sine theta as well, because that's the force pushing the person down the hill. So this is gravity helping out. It's going to reduce the amount of work they have to do times the distance, which is 2L. So the work the person will have to do, the net work the person will have to do, will be mbg sine theta minus 2m person g sine theta. Okay, there's another way we can do this problem. So that's solution method A. There's an alternative solution method that I'm going to go through, and that is conservation of energy. So as the person pulls the block up the hill, the block goes up the hill, goes to a higher potential energy, and the person goes to a lower potential energy. So all the work that the person's doing is going into the change in potential energy. Okay, so work is equal to potential energy, or energy. Let's do it right. Is it this way? Energy potential final minus energy potential initial. Okay, so there's two things that change the potential energy. There's the person going down and the block going up. So the block going up, how far will the block go up? So the height that the block will go up, it's going a distance L. So the height, the height that goes up by is L sine theta. So MB G L sine theta. Similarly, the person goes down the hill, minus MB or MP G 2L, because they go to 2L sine theta is the distance they go down. So by this method, we also get the same answer. I'm going to write it slightly differently in more compact form, as MB minus 2MP GL sine theta. So either way you calculate it, you get that for work. So this one we did from how much work they have to do by pushing friction against the ground. This one we do by how much work they're going to have to do to change the potential energy. Okay, so question number 4 says, what is the friction force between the person and the hill? Okay, so we can draw a free body diagram for the person. We have tension pulling upward. We have normal force pushing that way, force normal. We have gravity pulling down, person G, and presumably we have force friction pushing them down the hill. They're walking backward, they have to push up. This friction in principle could be pointing either direction. We'll figure out which way it is. If we get a negative, that means the friction was actually pointing up the hill. Okay, that'll be my free body diagram. For The person, I'm going to use a different coordinate system. I'm going to use that as x hat and that is y hat. I can do that. I'm going to use a different coordinate system for the person in the box. So I can do the forces in the x direction. So I have minus tension plus F friction plus mg, that's mass of person, g sine theta. And so that's the sum of the forces. There's no acceleration. We were told it's constant velocity, so that is 0. So the frictional force friction is equal to tension minus mpg sine theta. We weren't given tension explicitly in the problem. We've solved for it earlier, so I'm going to just put that in from earlier. So that was mbg sine theta over 2. So if I put that here, I get force friction is equal to mbg sine theta over 2 minus mpg sine theta. Force of friction is equal to mb over 2 minus mp g sine theta. You'll notice that this is this frictional force is the force we used, is the net force we actually used in the first solution method for the work. So that was that right there. That times the distance the person walks to L is how much work they did. So there you go. So this is the frictional force. I would like to point out that this is not necessarily equal to force. So force of friction is less than or equal to, and probably less than mu s force normal. Why is that? Well, because of the less than. The person isn't slipping presumably, so they don't need to do work. Or sorry, they don't need to be up to the mu s fn. We're in the condition where it's less than. So this formula here would only tell us when, how heavy of a box the person could pull up before their feet slip, or if how heavy they could be before they slide down the hill. Okay. Now we can look at this equation here. You can see this can be positive or negative. If the box is times the box divided by 2 is greater than MP, then the person has positive friction, meaning the downward. They have to pull the box up the hill. If MP is greater than MB over 2, then we get a negative value. That means they actually have to slow themselves down with friction because the tension isn't enough to hold themselves up by itself. Okay, so that is how you solve that part of the problem. I'll just circle all my answers here. You can do this method or that method for that part of that problem. And 2L is the distance they go, and that is the tension. And that's how you solve that problem.